Hello, and welcome to this GCSE Physics exam preparation video on atomic structure. Radioactive decay is random, and the decay of an individual nucleus cannot be predicted. But over time, a pattern can be seen of how long it takes for half the nuclei to decay. So we have our sample here, and after one day, half of our sample has decayed. After a second day, half of the remaining radioactive nuclei have decayed. We have a quarter of the original amount of radioactive nuclei left. And after a third day, we have only an eighth of the original amount of our radioactive nuclei left because another half has decayed. The half-life of a radioactive isotope is the time it takes for the number of nuclei of the isotope in the sample to halve, or the time it takes for the count rate, or activity, from a sample containing the isotope to fall to half its initial level. The activity is the radiation given off per second by a radioactive source. It is the rate of decay, and it is measured in the becquerel, capital B, lowercase q. Whereas the count rate is the amount of radioactivity detected by a Geiger-Müller tube, or GM tube for short. This is what detects the radiation, and it needs to be attached to a counter which counts the amount of radiation detected. Not all of the radiation given off by our radioactive source will be detected. A half-life graph shows how an isotope decays over time. It can be used to calculate the half-life of the isotope. You go to the top of the graph. Here we've got 80, our count rate is 80. Half of that is 40, so you go down to 40. That was the amount that will be left after one half-life. Go across to your line and then go down, and our half-life of this particular isotope is 1 day. Examining the difference in percentages of decayed to undecayed nuclei can give an idea of how old a sample is. This is net decline. To use this, you need to apply an understanding of half-life. For example, uranium-234 decays into thorium-230. After one half-life, there will be 50% uranium to 50% thorium. After two half-lives, there will be 25% uranium to 75% thorium. After three half-lives, there will be 12.5% uranium to 87.5% thorium. So if a sample is 12.5% uranium-234 to 87.5% thorium-230 or other more stable nuclei, then you know that the sample has undergone three half-lives. As the half-life of uranium-234 is 245,500 years, then the sample is 3 times that, which is 736,500 years old. Radioactive contamination is the unwanted presence of materials containing radioactive atoms on other materials, like hands or clothing. This is external contamination. The hazard is the contamination is producing ionizing radiation as it decays, and this can damage cells and DNA. The longer the exposure, the greater the damage. The amount of damage also depends on the type of radiation. So alpha radiation, which cannot penetrate through the skin, is much less damaging than gamma radiation, which will go straight through the human body. To decontaminate, then wash the contaminated area. Internal contamination happens if radioactive material enters the body. And again, the type of radiation alters the amount of damage that is done. Gamma radiation is much less damaging than alpha radiation internally because alpha radiation is much more ionizing than gamma radiation. Irradiation is different from contamination. It is the process of exposing an object to nuclear radiation. Strawberries are irradiated to kill things that cause decay. This means the fruit will last longer on the shelves, but it does not make the strawberry radioactive. It's perfectly safe to eat. Irradiation can still be harmful as it can damage cells and DNA. To reduce their exposure, teachers will use long-handled forceps to handle radioactive sources. Background radiation is around us all of the time. Sources are natural and man-made. Natural sources are things like rocks and cosmic rays, which are from space, and man-made sources are fallout from nuclear weapons testing and nuclear incidents. The dose that you get from background radiation depends on your location and occupation. For example, an aircraft pilot spends more time at high altitudes than other people, and so has higher doses of cosmic ray exposure. Radiation dose is measured in sieverts. This is a big dose, so millisieverts is used. So 1 sievert is 1,000 millisieverts. Nuclear radiation is useful for radiotherapy, which is where you use radiation to kill cancer cells, medical tracers, which test to find information about the internal organs. Both need gamma radiation, as this will penetrate the human body, which means that the radiation can be detected on the outside. Half-life is also a factor in choosing an appropriate isotope for the job. A short half-life gives out lots of radiation over a short period of time. So this might be more suitable for medical tracers where the radiation is needed to be detected outside of the body. A long half-life will be radioactive over a long period of time, so this might be more useful for things like smoke alarms where we don't want to be having to change them all of the time. Nuclear fission is the splitting of a large and unstable nucleus, e.g. uranium or plutonium. Nuclear fission is the splitting of a large and unstable nucleus, for example uranium or plutonium, and this gives out energy. Here we have a diagram that shows what happens in a fission reaction. So a neutron is fired at uranium-235. This neutron is travelling slow enough to be taken into that nucleus. It temporarily becomes uranium-236, which is so unstable that it splits the nucleus apart. We have 2 daughter nuclei produced, and on average we have 3 neutrons produced as well, and they carry away some of the energy in the form of kinetic energy. You also have gamma radiation released from this reaction, and that carries away large amounts of energy. Now, nuclear fission is useful because it forms a chain reaction, and that chain reaction can go on to produce lots of energy. And this energy can be used in nuclear reactors in a useful way. However, if the reaction is uncontrolled, large amounts of energy are released, and this is not desirable. Fission reactions are prevented from going out of control in nuclear reactors by using boron control rods. They absorb some of the neutrons, and this slows the rate of fission reactions. Fusion is different. Fusion is the joining of 2 light nuclei to form a heavier nucleus. Some of the mass is converted into energy, and that energy can be used to make electricity. So in this diagram, we have tritium and deuterium, which are isotopes of hydrogen. If we get them moving fast enough, they will collide and they will form a helium nucleus and a neutron, and lots of energy will be released, and that energy can be used to make electricity. And that's it for this video. Thank you so much for listening.